Right, so we did the customized knee implant, and we are optimizing for additive manufacturing and tight tolerancing. Our project introduction, same as the challenge that we were given, or challenge 1. The main goal here is that the process of getting a knee implant is that currently you do an entire knee implant, and that has very long lead times to be able to get the proper product to the customer, and it also takes a lot of time to recover from that process because of the amount of material that's removed, bone material, and the customized knee implant is trying to remove the process of having to go through that, and that way we get a quicker road to recovery and shorter lead times.
So following that purpose, we employed the following 3D experience applications. Powder bed fabrication was one of the biggest ones, where we were able to use a lot of the apps within it to figure out the path we were going to go and optimize a lot of the different variables in there. The additive manufacturing scenario allowed us to structure the thermal and structural simulation according to our challenge. So we could plug in all the parameters for temperature and build time, all the machine parameters as well. Digitized shape preparation gave us the deviation analysis tool, which was useful after we printed, so we could then check our simulated print model and compare it directly to the model we were given at the beginning to figure out how much distortion was evident through the print. Virtual to real shape morphing allowed us further analysis of the modeling of the printed part. We could create a vector field, and then that also gave us vectors for displacement as well as temperature and several other variables that were then used to make other models to do more comparisons and figure out exactly what was going on. These applications addressed the setup and simulation as well as the deformation analysis and all the modeling necessary to do all the changes.
So some of the limitations for our project. So we were given the manufacturing parameters. So effectively the laser sintering properties, so of the machine, the power recoding times, and build tray dimensions, and then material properties and initial conditions for temperature and heat transfer. And then we were also given mesh constraints in order to perform standardized models for our 3 different situations. And then what we changed was the part orientation. So we ran 3 different simulations using like a standard face down, face up, and slightly optimized angle setup on the 3 different build trays. So an example for one of our simulations is here, and it just shows what we were working with after performing additive manufacturing simulation. So there's an animation. This particular animation is for our displacement, which was our primary goal to minimize. So we worked a lot with this data in particular.
This was our first simulation. It was the one I was taking care of. Each of us worked with a different orientation of the tibia side. Figured orientation of the femur side. This is the tibia side. This is a solid part, and the bottom is flat. So one of the variables we tried to avoid changing is the orientation of the tibia. With the flat side on the bottom, post-processing would be much easier. It's a flat side, you just shave off or machine or surface grind all the support material on the bottom. So our max deformation on here was 1.37 millimeters. And here's just another image with the vector field overlaid to give more context of the bone coming up from the bottom. This is our femur print, my femur print, which was the first orientation. The contact surface was facing up, so in this way there would be no support structure on the implant surface, or the knee replacement surface. So where this was contacting the tibia side, it would be a clean surface to touch the other side. The only issue here would be all of the support structure is on an internal surface, so it would be a little bit harder to remove, as well as any that's not removed is directly contacting the patient's bone. We did find that the deviation analysis here gave us just under 1 millimeter of deviation.
And then we also ran a simulation with the contact surface down. For the femur
Actually,
implant.
this is the same one, just a visual of the bottom side of it. The deformation is a little bit different on the inside. You can see the max outward deformation is on here, on that inside, and as well as the other side, on the new side.
Okay. So we also ran face down, so then the contact surface up. And so there would be one easier, I guess, post-process for this particular orientation is that there wouldn't be any support structure on the inside surface on this concave this concave surface on the inside of the surface, or on the inside of the insert. So that would greatly improve post-processing and ease of manufacturing. But the problem is that I guess all of your support structure is on the bone contact, so most likely that wouldn't ever be a viable choice, assuming the as printed surface quality is good enough for medical purposes.
So this is my result that I came up with. We used a part orientation optimization tool in the print structure. We basically tried using their rule setup that we can optimize for the amount of support that we would end up printing and the amount of internal support we would end up printing. And this basically gave both prints a 45-degree tilt and then a slight angle, and it helped remove some of that internal support and then the majority of the support on, in I guess the left image, the leftmost print, which is the tibia side. And then along with that, when we did this, it helped remove a lot of the displacement that we had, and we believe this is due to the fact that our printing surface area is decreased in the horizontal plane, I guess. The leftmost picture, again, whenever we printed it laying down, we had a lot of distortion in the center of the tibia. And in this, we dropped the distortion all the way down to 0.22 millimeters, so almost a quarter of what the distortion was in the original laying down, which seems probably the most basic way to print it.
Okay, so further work that we would like to do with this project, if we were given the time, would be first to take the resulting models, so the deformed models, and then we already use tools within 3D Experience to basically perform a -1 gain on that displacement, and then create 3D models of what we expect the 3D model should be in order to print and reverse that deformation, so that the same deformation ends up creating a very tightly toleranced part according to the original CAD model. So what we would like to do is take those CAD models and re-enter them in manufacturing simulations, and then verify that the final results are very close, if not identical to the original CAD model. And then that would establish that we've maximized the tolerancing abilities of this software, and then we would use those results to create rules and determine what the optimized strategies would be for part orientation. So determine whether our hypotheses about changing the cross-sectional area and minimizing those large contact areas in order to minimize distortion, and then apply that to the 3D Experience software so that we can have a default setup for quickest, planning for any customizable knee implant, and then actually use these results to print a prototype and then evaluate it for its actual physical dimensional accuracy, see if our models actually are verified in the real world, and then determine whether the surface finish on the as printed parts is adequate for medical purposes, because if not, then creating a dimensionally tolerance part in the 3D manufacturing environment is, I guess, sort of irrelevant, because you'd still require post-processing to improve that surface, at which point you could change the final dimensions. But if possible, that would be the idea, is to determine that the result is as close to the original CAD model and as close to usable in the real world as possible.
Key takeaways, we got a great introduction to 3D experience. Like I said, we're from university, so this is really the first time that any of us have gotten to use it. We've used Dassault products in the past. We've used Abacus and some portions of SolidWorks, but this one was new for us. We got to use its in-depth additive manufacturing capabilities, and then with this open-ended challenge, we were rewarded with creative thinking and working late to get these concepts really put on the board. We recognize the industrial applications that this has, because we've seen we went and saw some of the talks here, and we see the scope that additive manufacturing really has and how this package could be applied in the field.
So I guess we'd like to thank Dassault for having us, and especially Mrs. Rachel Fu and Mr. Akshay for their personal help with us later last night and through the days to help us get our simulations operational. And then Dr. Shukla and Dr. Khan for coming and bringing us here and inviting us to get involved. It was a good time. Thank you.
Anybody have any questions?
Any questions?
Okay.
That's great. Did you want me to film anything else before you go?
No, I think that's it. But if I can have this on my computer so that we can show it to the judges at 5, is that possible?
Do you have an SD card?
That's a good question.